Welcome to Principles of Ecology. Today, we are exploring one of the most important processes on Earth, the nitrogen biogeochemical cycle. Imagine floating in the ocean, dying of thirst because you cannot drink the salt water. That is exactly how most living things experience nitrogen. We are swimming in it, but we cannot use it. Let us discover how nature solves this incredible problem. Now that we understand the basic premise, let us look at why this paradox exists. Our atmosphere is made up of nearly 78% nitrogen gas. We are literally breathing it in every single day. However, this atmospheric nitrogen is locked up in a tight chemical bond that plants and animals simply cannot break. Yet, nitrogen is a fundamental component of amino acids, which build our proteins, and nucleic acids, which make up our DNA and RNA. Without a way to access this nitrogen, life as we know it would grind to a halt. The nitrogen biogeochemical cycle is nature's incredible recycling system that transforms this unusable gas into a form that life can actually consume. Building on that idea, let us explore why ecologists care so much about this cycle. The nitrogen biogeochemical cycle is a continuous, dynamic process, circulating nitrogen among the atmosphere, land, and marine environments. Because usable nitrogen is so hard to come by naturally, it is often the primary limiting factor in agriculture and natural ecosystems. This means plant growth is strictly restricted by how much usable nitrogen is in the soil. This is exactly why farmers spend billions on nitrogen-based fertilizers. But there is a catch. If we disrupt this cycle with excessive fertilizer use, it leads to severe environmental issues like water pollution and massive dead zones in our oceans. So, how does nature actually unlock this gas? Let us look at the first of the 5 major steps: nitrogen fixation. This is where the magic begins. Specialized bacteria, which often live in the roots of plants called legumes, act as microscopic chemical factories. They pull the inert nitrogen gas directly from the air and convert it into ammonia. This is a monumental task because it breaks the strong bonds of the nitrogen gas, turning it into a reactive compound that can eventually be used by other living organisms. Without these tiny bacteria, the rest of the food web would completely starve for nitrogen. Now that we have ammonia in the soil, we face a new problem. It is toxic to many plants. This brings us to the second step: nitrification. This is a brilliant 2-step process handled by different sets of soil bacteria. First, they convert the toxic ammonia into nitrites. Then, another group of bacteria takes those nitrites and converts them into nitrates. Why does this matter? Because nitrates are the absolute favorite form of nitrogen for plants. They love to absorb it. This step essentially purifies the nitrogen into a highly nutritious, plant-friendly fertilizer, setting the stage for the next phase of the cycle. With nitrates now readily available in the soil, the ecosystem is ready for step 3, assimilation. This is the moment where nitrogen finally enters the macroscopic food web. Plants pull these nitrates up through their root systems and use them as building blocks to create plant proteins and nucleic acids. When a herbivore comes along and eats that plant, it digests those proteins and assimilates the nitrogen into its own body. Then a carnivore eats the herbivore, and the nitrogen continues its journey up the food chain. This is how the nitrogen from the air finally becomes part of the animals and humans walking the earth. What happens when those plants and animals eventually die? This leads us to the final 2 steps that close the loop. Step 4 is ammonification. When living things die or excrete waste, decomposers break down their organic nitrogen and return it to the soil as ammonium. This recycles the nitrogen so plants can use it again. But to truly complete the cycle, we need step 5, denitrification. Deep in wet, oxygen-poor soils, anaerobic bacteria take leftover nitrates and convert them back into inert nitrogen gas. This gas bubbles up and is released back into the atmosphere, perfectly balancing the cycle and ensuring the Earth's nitrogen is never permanently trapped in the soil. Before we move on to the mathematics of ecology, let us see this entire process visually. Look at this schematic of the nitrogen cycle. At the top, you see the atmosphere, our massive reservoir of nitrogen gas. Follow the arrows downward on the left. Nitrogen fixation pulls the gas into the soil and water, creating ammonia. Moving right, nitrification transforms that ammonia into nitrites and then nitrates. Notice the green plant in the center? That represents assimilation, where nitrates are drawn up into the food web. Below that, ammonification recycles dead matter back into the soil. Finally, follow the arrow on the far right. Denitrification pushes the nitrogen back up into the atmosphere as gas, completing the beautiful continuous loop. Now that we understand the biological steps, let us look at how ecologists measure the health of an ecosystem. We use the nitrogen mass balance equation. Conceptually, this is just like a bank account. We track what goes in and subtract what goes out. The term dN over dt represents the rate of change of the nitrogen pool in the soil over time. The first group of variables are the inputs. F is biological fixation, D is atmospheric deposition from rain, and M is mineralization from decaying matter. The second group are the outputs. U is plant uptake, L is leaching, washed away by water, and E is efflux from denitrification. If inputs exceed outputs, the soil is enriching. If outputs are greater, the soil is losing its fertility. Let us see this formula in action with a concrete example of a temperate forest. We are given specific values for how nitrogen enters this ecosystem. The biological fixation is 25 kilograms per hectare per year. Rain adds an atmospheric deposition of 5 kilograms, and decaying leaves provide a mineralization of 10 kilograms. We need to find the total gross addition of nitrogen to the soil. We choose the input portion of our mass balance equation because understanding the gross input is the first step in evaluating the site's fertility. By adding 25, 5, and 10, we find that the total input of nitrogen into the forest soil is 40 kilograms per hectare per year. This is the maximum potential nitrogen available for plant growth. Now that we have our inputs, we must calculate how much nitrogen is being removed from this available pool. The growing trees take up 20 kilograms per hectare per year, heavy rains cause a leaching loss of 8 kilograms, and denitrifying bacteria cause an efflux of 4 kilograms back into the air. We sum these losses to find the total output. We add the plant uptake, the leaching loss, and the denitrification loss. This represents all the natural ways nitrogen is leaving the soil pool. Adding 20, 8, and 4 gives us a total output of 32 kilograms per hectare per year. We will use this intermediate result in our final subtraction step to find the net balance. With both our total inputs and total outputs calculated, we can finally determine the ultimate balance of the ecosystem. We take our mass balance equation and substitute the values we just found. We subtract the total output of 32 from the total input of 40. This simple subtraction reveals a net change of positive 8 kilograms per hectare per year. What does this mean physically? Because the number is positive, the forest soil is accumulating nitrogen over time, making it richer and more fertile. This confirms that our undisturbed forest is acting as a healthy nutrient sink, building up its organic matter rather than degrading. While natural forests are often efficient, human-managed farms frequently struggle with nitrogen loss. This brings us to our second important formula, nitrogen use efficiency, or NUE. Conceptually, this formula measures how much of the expensive fertilizer a farmer applies actually makes it into the crop versus how much is wasted. In this equation, NUE stands for nitrogen use efficiency. The variable UC represents the nitrogen successfully taken up by the plants. Na represents the total artificial fertilizer added to the field. We divide the uptake by the applied fertilizer to get a fraction, and then multiply by 100 to convert it into a recognizable percentage. If applied fertilizer increases without a matching increase in crop uptake, the efficiency drops, indicating severe waste. Let us apply this efficiency formula to a real-world agricultural scenario. We are given that a farmer applies 150 kilograms of nitrogen fertilizer per hectare. However, the crop only assimilates 90 kilograms per hectare. The rest is lost to groundwater leaching and atmospheric denitrification. We are asked to calculate the nitrogen use efficiency to understand how wasteful this practice is. We substitute our given values into the equation, dividing the 90 kilograms of crop uptake by the 150 kilograms of applied fertilizer. This gives us 0.60. Multiplying by 100 yields a final answer of 60%. Physically, this means 40% of the applied fertilizer was completely wasted, which in real life causes severe ecological damage, like toxic algal blooms in nearby rivers. We have covered a lot of ground today, so let us reinforce the three most important ideas from this topic. First, the nitrogen biogeochemical cycle is absolutely essential for life. It transforms useless atmospheric gas into the very molecules that build our DNA and proteins. Second, this brilliant dance of elements is driven by microscopic bacteria through 5 distinct steps: fixation, nitrification, assimilation, ammonification, and denitrification. Finally, we learned that by using mathematical tools like the mass balance equation and nitrogen use efficiency, ecologists and farmers can track and manage the health of our planet's ecosystems. You now have a complete foundational understanding of how nitrogen sustains the global food web. Excellent work!